So, hello everyone, welcome to the particle theory seminar. Today we are very happy to have Sridip Pal from Caltech, who will tell us about universality in spin refined high-energy data in higher D CFT.
Thank you. Thank you for the invitation. Thank you for having me here. It's nice to visit Chicago, especially in fall. Today I'll be telling you about universality in spin refined high energy data in higher dimensional CFT. And in particular, by high energy data, I mean the high energy density of states. And the idea is to figure out the universal expression of high energy density of states and how it gets distributed among various spin sectors for higher dimensional CFT. So in 2D, we know that this kind of universal result follows from Cardi-like formula, where the high energy density of states depends on central charge. But in higher dimensions, we do not have modular invariance, and we do not have as such Cardi formula that follows from modular invariance. But today I am going to convince you that still you can do something, and in higher dimension you can write down some universal expression for high energy density of states, and you can also derive some result regarding how this high energy density of states gets distributed among various spinning sectors, even for higher dimensional CFT. So to set the stage, I will first tell you the stories from 2D and what kind of universal result we can gain in two-dimensional CFT for using modular invariance. And that will motivate our question for the higher dimensional CFT. And then we will do some path integral tricks to figure out the similar kind of universal results for higher dimensional CFT. So let us begin with the 2D case. So we are looking at 2D CFT, which is unitary and modular invariant. And as I was mentioning, in two dimensions, you have the famous Cardi formula, which basically tells you that the density of states, rho of delta, as delta going to infinite limit, is given by this universal expression, delta cube over Q. And the important point of this formula is that this formula doesn't really depend on what kind of 2D CFT you are looking at. Rather, once you give me the central charge of the 2D CFT, the high energy density of states is completely fixed. So this means this is universal and depends on a single parameter, which is central charge. And of course, like if you consider a compact 2D CFT, the density of states is really a distribution. So a proper way to interpret this formula is to take the density of states and integrate it over some small window. So you need to smear this density of states, smear over a small window. But the point being, the important point is, even after smearing over a small window, this thing only depends on the central charge, and hence this is universal. So in this talk, without this technique, like I will not go into technicalities of this smearing over a small window. So to make our life easy, we will phrase this universality in the canonical ensemble. So instead of looking at the density of states, I will be looking at the following quantity, which is z of beta, which is trace e power minus beta h. And I will be asking how this thermal partition function behaves in the high temperature limit. And the equivalent statement of this density of states formula is that in the beta going to 0 limit, this has a universal formula which goes like this. And again, the important point is that this expression is universal and it only depends on a single parameter, which is the central charge of the 2D CFT. And you can make it a little bit slightly more invert. So you can also turn on the fugacity corresponding to the spin. So you can evaluate the following quantity in the beta going to 0 limit. And again, you can show that this has a universal expression which goes like this. And to derive this formula, what you really use is the S modular transformation. So, which tells you that Z of beta is same as Z of 4 pi square over beta. So the idea is you take beta going to zero limit, which basically means this 4 pi square over beta becomes very large. And then everything gets projected onto the ground state from this side, and the ground state energy is given by this universal central charge. So this formula basically in 2D CFT tells you that there is a universal expression for the partition function in the beta going to zero limit. Now you ask a more sophisticated question. So you ask what happens for the following quantity. Say I want to compute trace e power minus beta h minus 1 to the power j. So this quantity weighs the spinning states in a different way. So because we have minus 1 to the power j, the even spins get a plus contribution and the odd spin states get a minus contribution. So in the microcanonical ensemble, roughly speaking, this proves some quantity of this form, the density of states of the even spin states minus the density of states with the odd spin. So this formula gives you the overall density of states, and this form, like if I can compute the beta going to zero limit of behavior of this quantity, this tells you how the rho even minus rho odd behaves, the fluctuation between various spin states. So this is some subleading information compared to this thing.
Sorry, J is an integer for you, you're not considering.
J is an integer. So everything what I'm going to talk about for most part of the talk is bosonic. So J is integer, and then I will briefly mention how to generalize to the fermionic. Okay. So now how do you compute this quantity? So to compute this quantity, we need to remember that the partition function is modular invariance, and the modular invariance is more than S modular transformation. So there are other group elements inside the BSL2Z. So in particular, given this quantity, I can use the following modular transformation, which looks like -1, 0, 2, -2. So this takes the modular parameter tau and maps it to minus tau to tau minus 1. So here you just, so the S modular transformation was of this form, 0, 0, -1, 1. And instead of this matrix, now you are using a different matrix. And if you use this matrix, then you can show that in the beta going to zero limit, this behaves like exponential 1/4 4 pi square over beta c over 12. And you can make it more slightly more involved. So by using a similar kind of matrix, you can show that trace e power minus beta h I omega j e power twice pi I p over q j in the beta going to zero limit behaves as exponential 1 over q square 4 pi square over beta c over 12. Now the important point to notice is that now if you look at this Cardy formula and this kind of formulas with insertion of -1 to the power j or insertion of e power twice pi p over qj, there is a universal factor that appears which is given by 1 over q square here. Here it is 1 over 4 compared to this formula. So this tells you something really important, that if someone tells you the leading behavior of the partition function in the beta going to zero limit, so if you know this quantity, if you know the central charge, then that you can, by using modular invariance, you can immediately predict the behavior of this kind of partition function with insertion of -1 to the power j, or in general insertion of e power twice pi p over qj.
Is that enough to solve for the asymptotics of rho of a fixed j?
No, not really. So if you look at, so if you want a formula which is for order 1 spin and large delta, then what you should do, you should take this formula and there do a Fourier transform and then do some asymptotics. So here, when I am saying row even and row odd, basically all the even states contribute. So you cannot just single out a single.
No, I know, but you know the asymptotics for all P and Q.
Yes, so
So
the
you can't use that information to solve for it as a function of J.
The tricky part is that there is a parameter beta, so this formula breaks down when this P over Q becomes comparable to beta. So you cannot just imagine doing all sorts of rational and then do linear combination, because at some point the formula will break down. So, but this gives you some rough estimate. So, for example, like you can take some linear combination of finitely many of them and it has some estimate, but you cannot go on doing this forever and claim that there is a formula for each spin. So now so in 2D we have this nice picture, and as you can see, this basically follows from the fact that we have a modular transformation, which basically tells me that the partition function is invariant under various modular transformation. In higher dimension, we do not have this thing, that we do not have modular invariance. But what I am going to show you that in higher dimension there is some sense, there is a sense of universality. And if you tell me some asymptotics of beta going to zero limit, I can still predict something about this kind of partition function. So in yes.
So in your first formula that had an omega, if
Yes.
omega was pi over beta, it would have given you also -1 to the j.
Yes, but the
You're assuming, I guess omega is kept fixed as
yes,
beta.
exactly, yes. So here omega is order 1 and beta omega goes to 0.
Yeah.
So that's is regime of validity.
Okay.
So you cannot just set beta omega to pi.
Yeah.
Because if you fix them, then as beta goes to 0, omega has to go to infinity. And that basically is away from the regime of validity of this formula.
And otherwise, there's no constraint on omega. Omega can be, because it looks like there's a pole, but omega can be large.
Here, yes. So the point is, if omega is on the real line in this axis, then this formula is valid for any order 1 omega, as long as you take some value and fix it and take beta going to 0 limit. But if you rotate it to so that this I omega becomes real, and then this pole will hit you, because then you will have e power minus beta h minus j, and then there is a unitarity bound.
So probably near there also.
Yeah, exactly.
So you mean this formula has some correction that is depressed by beta times omega?
Wait, which omega has correction?
Sorry, I mean this formula can have some corrections that's depressed by beta omega.
No, this formula is all the corrections in, so you should really think of this formula as omega being fixed. And then all the corrections are non-perturbative in 1 over exponential minus 1 over beta.
Oh, I'm just trying to imagine what happened, what breaks down with omega is.
So there will be, so basically there will be some resummation effect, and it's very hard to see how this resummation effect will happen and to give you this formula. Yeah, and later on, when I will tell you about the higher dimensional stuff, it will be more clear why this EFT breaks down and we need to do something more. So in higher dimension, the question is following that so first I will tell you that there is a beta going to 0 limit, there is an expansion even in higher dimension of this form. And so on. So this series for 2 dimension, this series basically truncates in the first term, so you have only one piece. And then you can insert some e power twice pi p over q j. And then I will tell you in the beta going to 0 limit, there is also an expansion, some other Wilson coefficients. And the main question is that, so in 2D, there is only A0 and A0 prime, and they are related by this 1 over q square factor. So in the question I'm going to ask whether in higher dimensional CFT, there is a relation between unprimed and the primed coefficients.
In higher dimensions, does unitarity force A0 to be non-zero
Yes, A0 is positive.
for every theory, non-zero, not just greater than or equal to zero, but no, but strictly greater.
Oh, that's an important question. I think that unitarity will only tell you is greater than equals to zero, and removing that equal to sign, I don't know any rigorous way of doing that.
But do you know any theory where it's equal to zero?
No. And in 2D, you can basically it's central chart, so you know it's radical.
Yeah, no, in 2D I'm fine, but yeah.
In higher G, yeah, so we are going to assume that A0 is positive basically. Well, this relation doesn't really depend on whether like, so I think you can say that A0 for our purpose, A0 is greater than equals 0 and
What's the argument that leads to this one, analogous to modular invariance?
this expansion. So first I will tell you that why this expansion exists using some thermal effective field theory.
Okay.
And then I will tell you, then I will basically rederive the 2D result using some effective field theory argument so that that proof easily generalized to the higher dimension, and then we will have a result. And in higher dimension, we will also ask whether there are some new features. So we will see that there are actually new features in higher dimension which are absent in 2D. And just to anticipate the result, let me write down the 2D result in the following way, which is log of trace e power minus beta h j in the beta going to 0 limit goes like 1 over q log trace q beta h I omega j.
Sorry, where's the general D in the formula?
So at this point, I have only shown you this formula is valid for 2D. Now, in the next part of the talk, I am going to tell you that this statement is also true in higher dimension. And in 2D, at this point, the statement just follows from modular invariance, but soon I will give you another.
There's no D dependence, is what I was asking.
Yes, here there is no D dependence, exactly. Yes, yes. So all the D dependence are hidden when you expand both these sides in the beta going to 0 limit, especially this one, because this expansion has a D dependence. So you can see that this will immediately predict that A0 prime would be A0 divided by 2 to the power D. P over Q is half. Because beta becomes Q beta, so you get a factor of Q from here, and there is a 1 over Q here. So for example, this immediately tells you that A0 prime is A0 over Q to the power D. So that's how the D dependence, and for D equals 2, you have 1 over Q squared. All right, good. Now I will give a very quick review of thermal EFT and how that expansion works. I believe Nathan gave a talk like a couple of months back on the thermal EFT, which was introduced by this paper by Nathan, David, Hiroshi, and Jeha last year. And so the way the thermal EFT works is following that the idea is that you can view this trace e power minus beta h I omega j as a partition function on SD minus 1 times S1, where there is some identification because of this twisting that there is an angular variable and there is a time tau, and theta goes to theta minus beta omega and tau goes to tau plus beta. So basically, as you go along in the tau direction by beta, you twist your SD minus 1 by some small amount. So this trace has a description in terms of the path integral, which is of this form.
Is the metric real for real omega, or is it not? Or
in this form, is everything is real? If you
Standard real metric
Yeah,
on
yeah.
that space.
Yes. So now the idea is that instead of SD minus one, you put your CFT on some arbitrary manifold M, and the idea is the metric on that manifold can be written down as G mu nu as in the Kaluza-Klein form. J dxi dxj, and then this partition function will become some functions of this AI, the dilaton phi, and the spatial matrix Gij. And then you assume that, so basically you are doing a Kaluza-Klein reduction along this time cycle. And if you assume that there is no zero mode under this Kaluza-Klein reduction, you can write down a thermal effective field theory, which is of this form, e power minus s thermal, and e power s, which depends on these modes, which only depends on the spatial manifold MD minus one. Now the idea is that your original CFT has like while invariance up to some while anomaly, so you can use that to your advantage and you can absorb this phi inside Gij, and that basically tells you that this is of this form, e power s thermal ai g hat plus some anomaly piece, which you can compute. And this g hat is defined as e power minus phi g. So now all we have to do, we have to take this S thermal and write down all possible terms which are coordinate invariant and matches with the scale invariance, and we will write down an expansion. And that precisely will give me that expansion. So let me write it down. So the expansion will be of this form, which is S thermal is dx square root g hat will be minus 1, and there's a coefficient minus f0 plus c1 r hat beta square, where r hat is computed with the g hat. And then you will have a second piece, which is comes from this a f square beta square, and so on. And now to compute this on SD minus 1, you just take this action and evaluate it on SD minus 1 with a spherical metric. So what does this thermal effective action do for you? It basically separates out the terms that it separates out the dependence of the background geometry and some coefficients f0, c1, c2, which actually depends on your CFT. So if you change your CFT, these numbers will change. If you change your geometry, this r hat, f hat, f, these terms will change. So in particular, if you evaluate it on this manifold, which is Z SD minus 1 times S1, then you will get this expression, which is volume SD minus 1 and in higher dimension you can turn on multiple fugacity, so there will be some omega I square, and then you will have f0 plus 2 this form. So this basically tells you that, so this is precisely of this form, the first equation I wrote on the top. That there are a bunch of coefficients and there is a beta dependence and every term is suppressed by from the previous term by a factor of beta square. Really right.
The anomaly terms are also even in beta, or can they have linear in beta expansion relative to the initial term?
Yes, so the anomaly term can be linear in beta. In fact, so the way it works that you should write H as some D plus epsilon, where epsilon is the Casimir, and then you should pick some scheme. And you should evaluate the both terms in the scheme. But those can be computed. So, and yeah, so those can be computed, but when I say S thermal, I do not mean the anomaly piece. I just mean the pieces that you can write down in this way.
But I'm trying to, the anomaly piece is the piece that depends on the higher dimensional central charges such as they are, A.
Yes.
So I'm just trying to understand the scaling of that term relative to these terms. That's subdominant relative to the F0 term?
Yes, I think it should be subdominant to the F0 term, but it can mix with these other pieces, and that is, yes, right. So one has to be a bit more careful about statements. Okay. So now we want, so this is our, so this basically tells you that if we have a manifold of this form, that some manifold times S1, I can use my effective field theory argument to write down some expansion of this form. So now I want to focus on the second term. In the second term, if I say P over Q is half, then you really see the identification is theta goes to theta plus pi and tau goes to tau plus beta, so it's not really a small twist. So I cannot really run this argument directly to expand this trace e power minus beta h e power twice pi I P over Qj, which is another way of saying that this expression is not valid to evaluate this kind of quantity here. So we need to invent some new technique to rederive this result. So that's what I'm going to do now. We are going to rederive the 2D result, but using some idea of thermal EFT, which mimics these ideas, but not exactly the same. Is there any question?
I guess I didn't quite understand why the thermal field theory is in this thermal field theory is invalid unless you take beta omega to 0.
Oh, because this expansion is really an expansion in so in this expansion beta omega is a small term, as you can see probably.
But the fields in the thermal field theory would not change, right?
Yeah, the fields will not change, but the point is that I guess we should not be able to, because this is a very large twist in the theta, so this Kaluza-Klein form, writing down in this Kaluza-Klein form is tricky.
Maybe it will become clear as you go. I don't get it yet.
Or another way of saying that there is a pole here, so you should not expect to go beyond this omega equals I. And then if you really want to do it for this thing, then as I was saying, beta omega is finite, so beta goes to 0, omega goes to infinity, so it will hit the pole.
That omega was a real number for you.
Okay, I see your point. Yes, omega was a real number there. But definitely these terms will be suppressed.
I think the high derivative terms are it's activating the high derivative terms.
Yeah, all the term of the same order. Like
So
there
you
is
need
no
something
suppression.
exact in F, is what you're saying?
Like this, I'm saying all the terms will all be on the equal footing, and you need some resummation.
The F terms,
What do you mean by F terms?
the ones involving the gauge field.
Oh, yeah, F terms. Yeah, sorry, I was thinking this. Yeah, yes, exactly. Yes. Right. So there will be some resummation. And you can see this also from this, like if you naively put omega equals something, you would not get back this formula in 2D. I don't want to delete everything.
Does the other side work better? Or no?
Or maybe,
No. Worse, maybe. Sorry.
yeah. It's okay. So now let us focus on trace e power minus beta h minus 1 to the power j for simplicity instead of looking p over q. So in 2D, like how can I express this thing? So this is nothing but a path integral over the following thing. Let me write here, which is, so I have a torus. But now because of this minus 1 to the power j, as I go from here to here in the tau direction, I also have to rotate the angular direction by amount pi. So this basically means this thing is identified with this. This piece is identified with this piece. And these two sides are also identified. So this is the path integral that I am doing. But now you can imagine that these two things are identified, and using the locality of the path integral, I can just cut out this piece from here and stack it on the top of this thing. Because these two things are identified, so this is now L over 2, this is L over 2, which is pi, and this is beta. So now I stack this on top of this. So this becomes this dotted line. This thing is identified with this thing. This is identified with this, and this thing gets identified with this thing. So now effectively I have a twice beta, the length of the time cycle, because this gets identified with this, and the spatial cycle is now L over 2. Now imagine you take beta going to zero limit, and this is of the standard form, so you can try to use the thermal EFT on this thing. So originally the Cardy formula was exponential, what? Twice pi over beta, twice pi c over 12. But now my beta becomes twice beta, so I have a factor of 2. And L becomes L over 2, so I have another factor of 2. And that precisely gives me this factor of 1/4 that I wanted. And then you can do the same thing for, if you have e power twice pi p over q, then you will basically have q pieces, and you cut them into q pieces and stack them on top of each other. So L would become L over q, the beta will become q beta. So there will be a factor of 1 over q here, 1 over q here, and we'll get 1 over q squared. And this precisely reproduces the 2D formula we had, just by doing the path integral. Now this argument is very general. It doesn't really depend on the fact that there is a actual modular group and there is actual modular invariance. So this we can run the same argument for higher dimension as well. And once we run this argument for the higher dimension, you will see here that there is a factor of 1 over q, which is coming from the fact that there is a L over q, or the volume gets divided by a factor of q. And this q beta comes from the fact that you are stacking q pieces on top of each other, which gives you this q times beta.
Sorry, I just missed something
Yeah.
in the even in 2D. So thing you land on still has these funny
Yes.
twists in time, right? But you can
Yes,
still
yes,
apply.
right, so yes, so that's some detail, so the idea is that in the beta going to zero limit, this identification doesn't matter. But then there can be anomaly and other things which can be sensitive to those things. So for example, in 2D, if you have CL not equal C, right, there is some extra piece which is proportional to twice pi I P over Q, CL minus CR over 24. And from the effective field theory point of view, you should be writing down some Chern-Simons term, integral of A. And those kind of terms can detect this kind of thing. But those behaviors are always subleading. So this prediction that A0 prime is A0 over Q to the power D, that prediction is always safe from those kind of things. So, yes.
In higher dimensions, you're no longer a circle, you're like.
Yeah, it's no longer a circle, yes.
So both J, you need to define like which part of
Yes,
angular
yes.
momentum. you
Yes,
need.
yes, of course, yes, yes.
But the scaling doesn't, like, you can't scale a circle down and glue it.
Yeah, so in higher dimension, the proper way of doing this, I'll tell, so this is the intuitive picture. In higher dimension, well, you can always define a rotation of angle and then you can rotate the sphere around that angle. So that's one way of saying things.
But you won't get a smaller sphere. Like, here you got a smaller spatial circle. But there's
No,
no way.
here there is no smaller spatial circle actually, because there is this weird identification. But the point is the length is L over 2. So a better way of saying thing is following, that what we are doing is the following thing. We are actually evaluating the partition function on this manifold, which is SD minus 1 times S1 Q beta modded out by ZQ, where the action of ZQ is following. It takes theta tau to theta plus twice pi P over Q and tau to tau plus beta. So this is the manifold on which, so earlier we are evaluating the partition function on SD minus 1 times S1. Now we are evaluating the partition function on this manifold where there is a quotient by ZQ. Now now the fact that in the beta going to zero limit, I can forget about this weird identification is same as saying that in the beta going to zero limit, I can approximate this manifold in the following way. ZQ times S1 Q beta. And now I apply my thermal effective field theory on this approximated manifold. And then this Q beta basically gives me this expression. And then there is a 1 over Q factor coming from this action of ZQ. So that's the approx. So whatever I drew here in terms of picture, in terms of equations, this means the following, that instead of evaluating on this complicated manifold, I am evaluating on this approximated version, and in the beta going to zero limit, they are equivalent. And of course, there will be corrections which basically can see the fact that this is a non-trivial bundle over this SD minus 1 ZQ because of this non-trivial identification. And if you have anomaly, then those terms can actually see this non-trivial identification. But the leading order terms will not see this non-trivial identification, and you are safe using this manifold as your approximation for this manifold.
Is there some a priori argument for that? The bottom counts operators at the tip of a singularity. And the top counts spinning operators, which seem qualitatively rather different, right?
Wait, why do you support? So there is something with the tip of the singularity, but
Well, SD minus 1 mod ZQ, if you fill that in, it's like if you did the radial map on that, it would give you tip of a singularity.
well, in the, for example, if this is S1 slash Z2, then there is no singularity. There is no.
No, the manifold is not singular, but if you imagine trying to do radial quantization.
I see what you're saying.
It's like, if you try to foliate R, RT by SD minus 1 mod ZQ, it'll have a singularity. So that bottom partition function is counting the. kind of CFT operators as-
Exactly, yes.
I was just wondering, that seems like a pretty non-trivial statement, that
Operators at the tip of a singularity are the same as asymptotically as spinning operators.
Yes, I think that's the prediction. Yes, exactly. Yeah. Yeah, I agree. As far as the asymptotic is concerned, they are the same. And now so this basically this immediately tells you that this A0 and A0 prime are all related, because for every beta you have to just scale with Q beta, and then there's a 1 over Q factor. So that basically tells you that A1 prime would be A1 divided by Q to the power D minus 1, and so on. And now there one more thing. So for example, you can take any free field theory, and in the free field theory, the partition function has an explicit expression in terms of Plathestic exponential, because you can just do word counting. And so you can explicitly evaluate these quantities and take beta going to zero limit. And then you can match up with our prediction that it exactly behaves that way. And not only that, you can also introduce some.
Is that true even for a free U1 gauge field? A free U1 gauge field would give you a scalar in the lower dimension without a thermal mass, so.
He's assuming there's a thermal mass.
Yeah, there is no, like, so I'm assuming there is no, like, when you do the Kaluza-Klein reduction, there is nothing else, there's this gap theory. Because otherwise there will be extra. So if you do not assume that, then there will be zero mass contributions, and you have to keep track of all those things. And they can pollute these things. So whenever we did for the, so when I said we did for the scalar field theory, sometimes we have to introduce some fugacity, like global symmetry fugacity, to kill the zero mode, and then run our argument. So so that was I was going to say that the general statement is you can introduce some U here, which is some global symmetry, and then there will be U to the power Q here. And in practice, that's what we use to kill the zero mode and then apply our argument. Okay, so there is one more subtle thing which I have not yet told you. So how am I doing at the time?
Actually, I have a complaint about what you just said. So
Oh, okay.
introducing these fugacities could have the opposite effect. They could actually, spontaneously break the symmetry, and then you would lose a thermal mass, even though you generally expect a thermal mass in an interacting CFT.
Sorry, say that again.
So you're saying if there's extra charges, I can add chemical potentials to these charges, and that can maybe help for some free CFTs.
Yeah, because then, like, if you have some extra fugacities, then as you go along the time cycle, it picks up some phase because it hits the unitary operator.
Right, but for interacting CFTs, it probably will do the opposite in that sense that it might actually spontaneously break that symmetry, and then you will have a zero mode.
Oh, yeah, but then, but in those cases, I am assuming there is no spontaneous symmetry breaking on, like, so it's yeah.
But in the case where you have a zero mode, is the scaling with beta different in the thermal partition function?
No, I think the only difference will be there will be extra contributions like constant pieces or log beta pieces. I think that's my guess. Yes.
But the leading piece you think is the same?
I think the leading piece will be same. You can check it, for example, again in the free scalar field, it just gives you some constant and log beta. Yeah, so so definitely there will be, so this argument definitely tells you that there will be some terms which follow this pattern in those cases. And there will be extra terms we need to keep track of. Okay, and now the subtlety I was going to, okay, so also one more point. So this is actually due to Luca. When Luca visited us, we were explaining him the results. So some of these results, specifically this argument about this stacking, actually also holds true for QFT. Because the only point where we are using the fact that this is a CFT is when we are expanding this, like when you are using the thermal effective field theory. But as a statement like this should also be true for any massive QFT as well. Because all we are doing is we are basically cutting down the path integral and stacking it on top of each other, and that step doesn't require you to have any conformal invariance or anything like that. So again, you can take a massive scalar field theory and you can check that this statement is true for massive scalar field theory. Now the subtlety. But now the circle is following is related to this manifold. So whenever this d minus 1 is even, for example, S2 modded out by ZQ, there will be fixed points of this manifold. So for example, if you take a sphere, there will be always a north pole and the south pole. So in the beta going to zero limit, we propose that there will be some extra contribution which are only supported on this fixed locus of this manifold. And those will give some correction to the expression for this log. And those we call is defect. And this is certainly a new feature that only happens in higher dimension. For example, if you do it for 2D, then it is S1/ZQ and there is no such fixed points, but starting from 2D, like S2, like that, starting from 3-dimensional CFT, at each odd dimension, you will have this feature, and there will be always a fixed point or even a fixed line or a fixed submanifold. And there the prescription is there will be new Wilson coefficients, and you should write down some thermal EFT or a defect EFT, which has only support on this submanifold. So for example, if you do it for 3D, then there is North Pole and South Pole, and then the contribution will look like the following. So it will of the form 1/Q, some constant, and then there will be terms like this. If
Where are you getting these rules? So you're quantizing a singular manifold now, so I might have been worried that actually the theory just doesn't make sense.
So this rules is, as such, this rules doesn't come from anywhere, like no other fundamental principle. So the thing is that because there is so there are two things. So we are assuming that once you reduce the theory, there are defects. So there is a natural way to write down some terms on those defects. And then we cross-check against free scalar field theories. And there you can see that there are extra terms which can be accounted for using this defect action.
But you could a priori construct that defect?
What do you mean by constructing the defect?
Well, you're saying that a spatial singularity can be modeled as some kind of defect insertion.
You mean whether I can define some defect OP and all this stuff?
Or anything in that neighborhood, right? I mean,
I
I wouldn't in general expect that we can do QFT on arbitrary singular manifolds.
But the starting space is not singular though.
No, but in the end, the space that he says, I approximate it as this singular
No,
space.
but I mean, in some sense, it's really whatever you should get as a limit of that non-singular starting point.
So this is in some sense is an approximation.
I mean, this kind of story shows up in string theory all the time also. Reductions like this, where there'll be some non-singularization in some hidden direction.
Yeah, the whole manifold is not singular, of course, because there is a theta and tau gets shifted. Like, yeah, the singularity is only there in the, and then all we are saying that one way to capture them is to write down these extra pieces that. So it's like this, that you are just by approximating by a singular manifold, you are making some mistake, and then you are correcting those mistakes by writing down some EFT on the on those fixed locus. So
What are the fields in that EFT on the fixed locus?
So that's what I was going. So it's basically the same fields. You have to evaluate on those particular points, and you have to keep track of the fact that they are invariant under the subgroup that fixes the locus. So you just write down, for example, this Vj, there's a constant piece, and then there you can evaluate the Ricci scalar. So it's the same field basically. but there are more restrictions because
No, but nothing fluctuating, no new fluctuating fields. Or somehow you assume that they also got masses.
Yes, exactly. That's an important point. Yes, so yes, we are assuming they also got masses. Yes, and
When you say Ricci scalar of that singular space, or?
no. So this is like the Ricci scalar of the full manifold evaluated at that point. So so you can evaluate the Ricci without the ZQ. You can evaluate the Ricci scalar.
Yeah.
And the ZQ is just a quotient. It doesn't change any local thing. And you just evaluate the Ricci scalar on that North Pole and the South Pole. So that's a finite piece.
The weird thing is, won't it look like an orbifold singularity locally? Which,
Yeah, definitely in the limit that
Yeah.
during the approximation. it's some
yeah,
kind of
so
multiple.
to your point, the string analog of this, we don't know how to do this.
Yeah.
Well, I mean, we know how to go from there to there, but not
Mhm.
write down something here that directly.
Wait, but I'm confused. The R hat would be but R hat doesn't have any beta dependence. So you are just evaluating the R hat on the top and on the S2 on the North Pole and the South Pole.
Maybe because it's higher dimensional, you see the singularity in a different curvature invariant, I'm not sure.
No, the string analogs are not SD-1, but things like R4.
Okay.
So just in some cases, some inversion on R4 and a shift, say, in the certain direction. So it's non-singular.
So this is like C2/Z2 kind of structure.
Yeah, exactly. So C2 mod C2 on its own would be okay in terms of the string theory. But if you couple it to a shift in, say, the M theory circle, it's non-singular. It's exactly this. But we don't know how to describe it in string theory, which is the reduction.
I see.
It's weird.
Okay, in this case, in practice, what we do, we just evaluate the R hat on the sphere and then we just evaluate it, and that's a finite number. So it's a constant basically.
Yeah, then it's just Q divided.
Yeah, exactly, yes, exactly. So nothing really special happens. So one thing I wanted to mention here that so you have a bunch of terms. So now you can ask that whether there is some prediction that it makes. So first of all, in the free scalar field theory, you can check that these kind of terms are present. And then you can also do one more thing, that on the S2 there is a contribution from the North Pole and the contribution from the South Pole. So effectively for 3D, you will this term here will look like Q beta omega. Sorry, so let's say I do P over Q is half. And let us focus on this piece. And this piece will give some contribution of this form, A1 half minus A1 minus half. Now in 2D, in a bosonic theory, that rotating by pi in this way or that way is the same. So this effective field theory tells you that this term should not be present for a bosonic theory with P over Q half. And again, we go ahead and check for the bosonic theories, you will really see that this term is absent. So that's a small prediction of this defect action, and you can see it works. And another comment to make is that if you evaluate this on the S2, you will see that this defect action doesn't, at least in 3D, this defect action doesn't have any pole in omega. And then there is a physical way of thinking about it, is the following, that in your original effective action here, there is a pole in omega because it's related to the sphere rotating with the speed of light, the equator, the great circle. But when you are thinking of the defect action on the North Pole and the South Pole, there is nothing to rotate. So there should not be any, by the same argument, there should not be any pole in the omega, and you literally see that the defect action is regular or smooth in the, as far as the omega dependence is concerned. And in higher dimension, you can play the same game. There will be multiple omegas, and then you can have more detailed structure of what is the fixed locus. And the basic idea is again same, that you just write down all possible terms which are invariant under the rotation which fixes the locus. now I will, okay, I am running out of time, so I will end with two more comments. So one comment is about fermions. So fermions you need to, so you can again do the stacking trick, but you need to remind yourself of the antiperiodic conditions. So once you stack twice, that basically antiperiodic becomes periodic, so you have to insert -1 to the power f. So that's one way of thinking about the fermions. You have to just keep track of the boundary condition. Or another more clean way of thinking about this is like think about this insertion e power twice pi p over qj as a group element of the spin group, and then e power twice pi ij is -1 to the power f, and then you run the same arguments thinking about those group elements in the spin group, and then this statement is true in the same way. But then you cannot think of them as a rotation group, rather you have to think about the spin group. So that's about the fermions. And another statement is holography. So you can ask whether this says something about the holography, or whether you can construct some black hole solution which basically computes this trace e power minus beta h e power twice pi p over qj. And indeed in ADS3 this is some SL2Z image of the BTZ black hole, because I am doing some SL2Z transformation. And you can also construct this solution in the following way, in this stacking procedure. Or so what you do the following: you construct a solution in the bulk which is dual to this. So you extend the geometry, and then there is a quotient by ZQ, and then you extend this quotient in the radial direction. So as long as there is no singularity in the SD minus 1 slash ZQ, for example in ADS3, the solution is smooth. But then there is a problem if you are in odd dimension. Then at the tip of the cigar, you will have some orbifold singularity. And then the prediction is that there will be some mechanism which resolves that singularity, and that mechanism should also give you these extra Wilson coefficients. But at this point, we do not have any prediction for those cases from the holography side. And if we do not have this, if this manifold is smooth, if you arrange for that scenario, then everything is also smooth in the bulk, and then there is actual solution. And you can evaluate the free energy in that solid black hole solution, and again maths. Then it basically tells you all the Wilson coefficients I wrote there gets fixed by the black hole solution. So to wrap up the full thing, the main punchline is the following: that even though we do not have modular invariance in higher dimension, just by using this stacking argument, if someone tells me the beta going to 0 limit of the canonical partition function, I can also predict how the grand canonical partition function will behave. So these two lines, this prime and unprimed, are indeed related, and they are related by this relation. That's it.
I mean, relating to the last thing you said, based on this singularity, there seems to be missing numbers from the regular partition function to the grand canonical partition function. Like there are additional numbers in the grand canonical partition function that are missing from the original one, right? These Wilson.
Yeah, they are new Wilson coefficients. Yes.
Is there a way to predict them from the original one, or are they new numbers you need to introduce to the EFT?
Well, if you are all powerful, can you evaluate the partition function? Then yes. Otherwise, yeah. So you are asking, given a CFT, how do I compute these quantities, these Wilson coefficients? Is that the question?
Sure. Or are they related in some way to the normal high energy, high temperature partition function, right?
But then you can ask the same question about the. So let me understand your question. So you can also ask about these coefficients, right? Are you asking? So is your question still valid, or is your question still about these coefficients A0, A1, A2?
My question is, okay, knowing A1 and A2, let's say the first few, you can predict the first few, A1 prime and A2 prime in 2D. But it seems like you can't in higher D because you're missing some knowledge, you're missing some Wilson code.
Yes, I agree with you, yeah, so at the first term is okay, because this defect action is always subleading.
Okay,
And from the second term onwards, there is a one part which we can predict. And then there is the other part which is really we need to know something more, yes, I agree.
So it's not universal, you mean?
Yeah, it's not universal, it's less universal, let's put it that way. I mean, yeah, so in some sense, you can also say that this is less universal than 2D, because in 2D you know the central charge, but in higher D you do not know. Yeah, but really the main point is that you can do this stacking argument and you can predict something. There is some part which is predictable. And you can always make sure, at least in even dimensions, you can always make sure that you quotient out in a way so that there is no defect, and then you have the full prediction. And non-perturbative, I mean, at a perturbative level. And of course, there are non-perturbative correction which goes like exponential minus 1 over beta.
There's no more questions, I think that's pretty good.